Hey, my name is Harsh and this is my Lab 3 demonstration. So right now we have an enabled flip-flop. This circuit has a 2-bit 2:1 multiplexer and a D flip-flop. The D flip-flop working is it displays whatever is at the input. If D is 0, Q is 0. If D is 1, Q is 1. So how this works is we have taken D as input and enabled to control this 2-bit multiplexer. This A is the previously stored output and B is connected to D, which is our input. This is clock signal, which so the D flip flop gets triggered only when clock is 0 to 1. So it controls the output. Let's start it. If D is 0, enable is 0, we get A, which is 0. So no matter what we do to the clock, we get 0. If enable is 1, we get B, which is 0, we get 0, we get 0. When D is 1, enable is 1, we get B. B is the output Y, which goes to the flip flop. So right now it's 1. When clock goes from 0 to 1, it displays 1. When clock returns to 0, what we can see is even if I do enable 0, the last word input, the last word output goes back to A. So right now we have A. Enable is 0, which should display A. So we are getting A as the output when clock runs from 0 to 1. So this is how the circuit works. So the next circuit is this 4-bit register. This is like the previous circuit, but it has 4-bit inputs. We are using a 4-bit 2:1 multiplexer. D as the input, enable to control this multiplexer. Here we have this clock, and this is asynchronized D flip flop. It works like the previous flip flop, but it has two features extra, which is set, which is preset and clear. Since we are not using preset in this circuit, so we have grounded preset. So the clear feature works if clear is high, which is 1, the output becomes 0 no matter what the input is. So if we simulate this circuit, we see we take D as 5. Enable is 0, we get A, which was 0, we get 0 at the output, no matter what. Enable is 1, okay. So if enable is 1, we get B, B gets here. This is a splitter, we get 0, 1, 0, 1, because that's what 5 is. These input goes to these asynchronous D flip-flops. So here we get D0, output is 0, D1, output is 0, D0, output is 0, D1, output is 0. The reason the output was 0 is because these D flip-flops haven't been triggered yet. When clock goes from 0 to 1, they get triggered. So we had 0 here, we got 0. We had 1 here, we got 1. Here we had 0, we got 0. Here we had 1, we got 1. The clear feature when right now the output is 5. So this 5 gets stored back into A. If we change D, the A will remain 5. So if we reset it, it will all become 0. So when we reset it, clear gets sent 1. No matter what was at the D, we get output as 0. So this is how this 4-bit register works. The next circuit is this. This is a program counter. So what it does is it does what it says. It counts. We have a 4-bit register. We just saw what the 4-bit register does. If enable is 1 and clock is 0 to 1, it counts 1. Clock goes again from 0 to 1, it counts again. Again 0 to 1, again 0 to 1, again. We have reset. If we click on reset, circuit becomes 0. We can see that it is actually happening because we have an incrementer here. This incrementer increments whatever we get last output. Previously initially it was 0, we got 1. So if I enable this, I start, it was 0, I take the clock from 0 to 1, we get 1, D gets 1. So while the reset is 0, clock 0 to 1 gives us 1. Now this 1 is back again to the incrementer. and we take 0 to 1 again, we get 2. This 2 is back again going to A of the incrementer, again 0 to 1. This flip flop triggers. This 4-bit register triggers and gives us the output from this incrementer again every time we take the clock from 0 to 1. The reason we are using this is, well, this is actually supply voltage. This is to give the incrementer always a high signal, which is 1. This will always give the incrementer here 1. So we don't have to switch from 0 to 1. We actually don't want to switch, since the incrementer does, all it does is increment 1. So we always want 1 here in most of the cases. So we have this one. So this is how this circuit works. Now let's move on to the next circuit. So this is my 4-bit register waveform diagram. This shows that it works perfectly fine. Now let's move on to the next circuit. So in this circuit, we have a programmable RAM. So the A is a RAM module with separate inputs for storing and output for reading the stored data. The D is data in the data to be stored in the RAM. This is stored. This is to store the data, and this is clock pulse. This is to initialize the data. If this input is high, the output is activated and the data is visible at the output. So this is these are inputs. This is address. This is data in. This is write, and this is the clock pulse to activate the clock. Let's see. When address is 0, we can see, since the ID is always an active or high, we can see 3 at the output. So if I change it to 1, we see that at data address 1, we have 5 stored, so it displays 5. If if I want to write at if I want to write 8 at a memory location, let's take 3, then all I have to do is turn on write function and then give the clock pulse from 0 to 1. So if I turn everything back to normal, what we can see is at 0 we had 3, at 1 we had 5, at 2 we had 0, and at 3, which we just told, we have 8. So this is how this programmable RAM works. Let's move on to the next circuit. So this is our last circuit, which is actually a combination of all we have done up until now. In this circuit, it's a brainless CPU. It's brainless because we give the commands by ourselves. We have data inputs here, and it does somewhat the functions of CPU. So we have an ALU unit, which stands for arithmetic logical unit. We have a 4-bit register, a 4-bit 2:1 multiplexer, a programmable RAM, which we just saw, and a 4-bit multiplexer again. So this is acting as our data mux, this is acting as an accumulator mux, and this is acting as the accumulator. This ALU output is marked as ALU out. This 4-bit register output goes to accumulator output, and it also goes to the B for the 4-bit multiplexer. And this output is the data bus, which goes into the programmable RAM to store data or read or write, or mainly to store it, which goes into this one, 4-bit multiplexer. So how this works is, uh, let's see first the data inputs. We have data in, we have address bus. So whatever at the address we can display it, data in to write at whatever address we want to write. We have invert arithmetic and pass feature of the ALU. Invert arithmetic and pass. This is load the accumulator to get our output at the accumulator output. This is accumulator to data bus. This is actually to get whatever we had at the accumulator at the data bus, so we can write it. This is a reset feature to actually reset the outputs. This is clock to give the clock pulse from 0 to 1 to get the desired output. This is write feature, which we talked about in the programmable RAM. This is to write at whatever address we want to store through the data and feature. We can write it by giving the clock pulse 0 to 1. And this is to read. So this read goes in this one, so we can read whatever is at the address bus. So let's start it. Since the address bus is 0, let's follow the path. This 0 goes up until here into the address of the programmable RAM. We know it is always, we have taken it as always active or high. The ID was high, so it will display the output as it is. Uh, whatever at the, it will display the output, whatever was at the data address 0. So as it was 3, it will show 3. But since this data marks this 4-bit multiplexer, we have to display B. Since it is 0, we know it will display A. So let's turn it on, which is the read feature. So this feature helps us read whatever is at the data bus address. So right now we had 3 at B. This B goes to the output Y when we turn select line to 1. So this 1 goes here. Since we had 0, this multiplexer gives A output, which is 3 again. So we get 3 at the data bus. As we can see, this data bus is going back all the way to A of the ALU unit. Since we have A here, now we have to get the output at Y to get it at the ALU output. As we know, ALU does many functions, but one of the functions is if we want to get the direct input at the output, we have to use pass feature. This bypasses all the functions the ALU does and displays A at the output. So right now we had 3 at the output Y, which is 3 here at ALU out. So now since we have ALU out, we have to load it to the accumulator so we can store it to B, since we are using B as a storage. So this this 3 goes into 4-bit registers D. As we know, it displays whatever is at D, it displays at Q when the clock pulse goes from 0 to 1. Let's enable it first. Let's load the accumulator. Now let's give the clock pulse 0 to 1. When we give the clock pulse 0 to 1, it stored 3, it displayed 3 at Q, and we got 3 at the accumulator. Now we can do same for the data address 1. When we have data address 1, this goes here, address 1, we can get the data output. We are getting right now 1, which is 5. So we are getting 5 here. 5 is going to be, we already have 1. 5 goes back here. We have 0, so 5 goes on to Y. 5 comes to data bus. 5 goes all the way to A. It's the same like we did earlier. So right now we have B 3 and A 5. Let's close the pass feature since we want to add. So we know to add A and B, we have to turn arithmetic to 1. So we have 8 here. What we also want to do is to write this at a data address. So what we are going to do is load it, send it to the data bus. So right now we have 8 here in D. We know we have to give clock pulse 0 to 1. Since it is already enabled, we give clock pulse 0 to 1. We have 8 here. 8 goes straight to the accumulator as well and to the 4-bit multiplexer. We want B now as the output. Select line is 0, so we turn it on. So accumulator to data bus is on. So now we get 8 at the data bus. This goes into the data N. We can change the data address. It goes all the way here. We can change it to 2. So let's store our addition at 2. So data N is 8, address is 2. What we can do is turn on. Let's close. Yes, let's write, and then let's give it the clock pulse 0 to 1. So what we see is now it is stored. Okay, now at address bus 0 we have 3. At address bus 1 we have 5. At address bus 2 we have 8. Now let's see the subtraction. Now let's take it again 0. So for subtraction, we see the 0 goes here, address bus, it gives 3 as output, 3 goes here into B, we want to display B, we have taken select line 1, we read the output as B, which is 3, 3 comes here, select line is 0, we get 3 at the output, this 3 goes all the way back to A, now we have 3 at the ALU where we wanted it, but let's store it to B, so we just pass it as the output, we get ALU out 3. This goes to the 4-bit register, which is the accumulator. So we just enable it, load accumulator, give it clock pulse 0 to 1. So we have 3 at the accumulator. So now let's do 5. Let's take data address 1. Data address 1. This goes to here. Data, it reads the data out as 5. So this goes here. 1 B displays at the output, which is 5. 5 goes to A. Since select line is 0, we get 5 as the output. Data was 5. This goes all the way back to A. So right now we have 5. Let's close the pass feature. Right, right now we have 5 at A, 3 at B. It's 1 because, as we know, right now it's doing bitwise AND. So it's showing just 1. So this A and B. A is A is 5, B is 3. So to subtract, we first invert and then we add 1. So we get our output E, which is B minus A. 3 minus 5 is E in hex. So this, let's load it to the accumulator. So let's enable, it's already enabled, give it the clock pulse 0 to 1. Now it goes to Q. So since Q is E, this goes to this orbit multiplexer or accumulator mux. This B is E right now, but we are choosing A. Let's load accumulator to data bus. So it's A, we get B at the output, we get E. Now data bus is E. Let's change the address to 2. Let's change the address to 3. We already stored at 2. So right now address is 3 and data N is E. So let's write and give the clock pulse 0 to 1. So now we have written at 3 location. Let's check. Let's close these. Let's let's see at 0. Let's read. At 0 we have 3. At 1 we have 5. At 2 we have 8. And finally at 3 we have E. So this is how this brainless CPU works. And one thing that I missed up earlier was we cannot read and write at the same time. So we have to close one when we do the other. So this is the working of this brainless CPU circuit. My lab 3 ends here. Thank you. Bye bye.
यार तू इतनी धीरे बोल रहा था मुझे नहीं लगता वीडियो आया कुछ
This is finally our brainless CPU's waveform diagram. This shows that all the functions that we performed are right as we can see. So this marks the end of the lab 3 and thank you.